This is actually nowhere near as bad as it looks. The only reason I have this is because my eyes can't focus in the same place at the moment, which means that if I have both eyes available, I just see two lots of distorted. So this is, if you see me outside getting coffee, I probably won't even have this on. I just needed to be able to read my notes. So this is not a problem. It just means I can actually read what I was saying. And by the way, I apologize if last Thursday was a bit strange. It was the first day this had come on, and I was a little bit panicky trying to get through the lecture in one piece. So Thursday wasn't my best effort, but we're back on steady ground now. All right, red light, let's start. Hello, welcome back everyone. You've got me again. I hope you enjoyed. Welcome back. You've got me again. I hope you enjoyed yesterday having Robbie. If you liked Robbie's style, he teaches the third year PDEs course, which follows on directly from this. If you particularly enjoy the second half of the course, that's certainly something you might want to look at. Also, he was one of the people who helped decide what content went into this subject, so if there's anything you want to yell at someone about, yell at him. No. It's all good. I hope you enjoyed yesterday. Yesterday, you went through a bunch of multiple integrals, just applications reminding you how it all worked. If you have looked in the online notes, you will notice that I've posted a lot more than was taught. Basically, the plan for yesterday's lecture was just to write out a whole bunch of multiple integrals and then to pick on the day which ones I wanted to do. So if you want a bunch of interesting applications and practice ones, there's a lot more in the filled out notes than we went through in class. Okay, but now we're moving on because this class is called Vector Calculus. And you might have noticed that we have done some, but not a huge amount of vector calculus, and it's time to change that. So we're going to move into an idea of how are we going to describe curves in space with the eventual intention of being able to integrate along curves in space. So by now, through the multiple integrals process, you've learned that we can parameterize these integral curves, and integrals don't have to just be pick an axis and integrate along it. You don't just have to integrate along x. In fact, by changing your coordinates, you could come up with nice shapes and all manner of things, and this sort of suggests, well, why don't we go back and think about what that means for one variable integrals-ish. So we looked at multiple integrals and we said these are a map from Rn to R, which is to say it takes a shape in space and spat out a single number. Okay? A function in space, you integrate it over some volume, and what you get is a number. Well, a lot of really important vector operations actually go about the other way, and we have seen things that have taken individual quantities and spat out vectors, for instance, the gradient operator. So let's say, well, why don't we think about maps that go the other way, and we're going to go all the way back to week whenever we did this and talk about parametric curves, curves in space. So I've done R2, but it can be R whatever. And I'm going to say, well, we have some curve in space, okay? And there is some point on the curve. Now, how far I've gotten along this curve can be parameterized by a single variable t. Okay, and the output of this curve, which I'm going to call sigma of t, is equal to x of t, y of t. I told you we'd get back to doing stuff like this. So the idea is I give you one number, and then what you do is give me a point in Rn. And parametric curves are great. We can weave them around. In the seminar last week, we drew a DNA, whatever. And we can, of course, it's a curve. We can integrate along it. It's a totally fine thing to do. So that is what we are going to talk about doing this week. And then next week, we'll start to think about a slightly bigger picture. But we need a few more tricks up our sleeve before we do that. Now, this is not my first rodeo. And I happen to be aware that students always find parametrization of curves to be a bit of a dark art. So let's talk about some small complexities. Say I want to find two parametric curves for this ellipse. Because parametrization is absolutely not unique. I can say, well, if I give you the number t, it tells me I've gone along this far, but if you pick t in a different way, maybe it tells you it's gone this far. Let's see an example. So if I have an ellipse, there is a very obvious parameterization, more or less, which is that sigma of t, which, recall, gives me the x-coordinate as my first value and the y-coordinate as my second value. I'm going to say is a cos t and b sine t. So when I am at t equals 0, my x-coordinate is at a and my y-coordinate is at 0. So if I'm at t equals 0, I'm here. And then if I move around up to t equals pi on 2, well, at t equals pi on 2, my x-coordinate is 0 and my y-coordinate is b. So I've moved all the way up to here. So I've continued around this way. Here I'm at t equals pi on 2. And I can keep going around all the way to pi. And I've parameterized my way around this ellipse. And if we want to check a parametric curve, we can. I have the Cartesian equation for ellipse, so I can just substitute in the coordinates of my curve and see what happens. Okay. So an ellipse is x squared over a squared plus y squared over b squared equals 1. If you ask your grade 9 cousin that, that's what they will tell you. And then what I do is I take my x and I substitute in what I know x to be in terms of the parametric coordinates to get a squared cos squared t over a squared plus y is b sine squared t, b sine t over b squared, which is equal to cos squared of t plus sine squared of t, which happily is equal to 1. So this works. If you have some condition that you know defines your parametric curve, then you can use a trick like this to see what it is. But of course, it's not unique. I want you to take 15 seconds, talk to your neighbor, and come up with a different parameterization. It doesn't have to be very different. Don't go wild. But have a moment. Say hello. Five, 4, 3, 2, 1. Okay, who wants to volunteer their friend's parameterization? Yes.
This guy said a plus 2t, 2 pi plus t.
Yeah, that would work. So the one I have written down is something not dissimilar, actually. X of t, y of t, which is equal to, I said a sine of 2t, b cos of 2t. So not far off. Yeah. And this works a little differently, right? When t is at 0, x is at 0, and y is at b. So at t equals 0, it starts here. And then it continues around, but at double the speed. So in fact, at t equals pi on 2, it's all the way down to here. So it's going twice as fast and starting at a different place. These are both totally valid parameterizations of this curve. And one thing that's going to be a very important result, and probably the first thing we do next week, will be showing that when we evaluate these integrals that I'm talking about, they will actually be independent of the choice of parameterization, but we'll get to that down the track. So parameterization is a choice. Yes?
So it could be any, it could be like a sine of t.
It could be, yeah, that would work. It would change the speed at which it travels, but it wouldn't change the curve which it traces out. That's exactly right. And that is typical of parameterization. So I have here space for us to do a quick check. We have time, so let's do that. X squared over a squared plus y squared over b squared equals 1. So a squared sine squared 2t over a squared plus b squared cos squared 2t over b squared equals 1. So we get sine squared 2t plus cos squared 2t equals 1, tick. Good. Both of these parameterizations sweep out an ellipse, which is great if I want to integrate along an ellipse, which is often not an unreasonable thing to do. So, given some curve in space, we've talked about parameterization already, and I know it's something students found a little bit difficult. There is one very important fact about curves in space, which is that its derivative is a vector that is tangent to the curve. And of course, we used this fact to define our tangent space. So this is a fact you've seen before. The derivative is a vector that is tangent to the curve. Sigma dashed of t, which is simply equal to the element-wise derivatives, x dashed of t, y dashed of t, z dashed of t. At any given point, it tells me what direction I am traveling in. And it also tells me how fast I'm going, which is to say the derivative with respect to t can be thought of as the speed in some way. How is my position changing as my parametric variable changes? So what I have here is a function whose input is t, one variable, and whose output is sigma of t, which is x of t, y of t. And take those together, sigma is a map from R to Rn. Parametric curves can weave through space. We've drawn them in 2 dimensions because it's very hard to draw in 7. But there is absolutely no reason for these curves to be restricted to 2 dimensions other than writing problems that are sensible. So these are going to be our bread and butter today. We're going to be thinking about what it means to integrate along these curves. However, it's a bit of a tricky thing to conceptualize because often we'll just say, you know, define some parameter, and it can be a bit tricky to know what the right parameter is. If I gave you no information other than what's there and said, hey, what's a sensible parameterization for t? Now I want you to talk to your neighbor, take 10 seconds, and come to an answer, and I don't necessarily expect you all to come to the right answer, or the answer I'm thinking of. But have a chat. What's a sensible parameterization of t, of the curve? All right, I'm going to give you 5 more seconds. Maybe a little longer. I like that you're talking about the work. Probably. All right, let's finish that up. A sensible choice of a way to measure t. Anyone got any ideas? Be brave. Someone from this half of the room would be fun. Putting the spotlight on you. No? That's half? Yep. Exactly. If I tell you how far along the curve you've gone, you can probably point at where you are, right? If I say you've gone 1 unit, maybe you're there. If I say you've gone 4 units, maybe you're here. So maybe arc length, which is something you've definitely calculated in your life before, I checked, is something that you can start to think about. So if sigma is a parametric curve between A and B, then the length of this curve is defined as, and this is a slight weasel word here, I'm not calculating something, I'm actually defining arc length here. This is a definition, which is that the length is equal to the integral from A to B of the square root of the sum of squares of its coordinates. Easy enough. Of the derivatives, sorry, derivative squared. X dashed of t squared plus y dashed of t squared plus z dashed of t squared dt. This is the definition of arc length. And if we want to write that in a slightly more compact notation, a to the b times the norm of sigma dashed of t dt. Now this starts to matter because this is a vector quantity, it has a norm, it has a size. Essentially this is saying the integral of how big the derivative is. If the derivative is very high, things are moving very fast, you cover a lot of length. Sort of makes sense in a circular way, but if we want to not be circular, then we've got to start with a definition, and this is a good definition with which to start. So, let's talk about reparametrization and say, well, in this case, changing the parametrization but following the curve, what effect does it have? Because there are two things about the derivative that can change, about its direction. Two things about the curve that can change, its direction and its magnitude. We would like very much for the parametrization to preserve something. So suppose we have some sigma of t, and suppose that sigma dash is never 0, just to avoid any problems. Then for any t in a and b, we can define a new parametrization, t equals t of s. So I'm interested in s, but I'm defining it this way for convenience. So I'm saying there's a relationship between t and s. Basically, as I move from one end to the other, both t and s are clicking up, but they're clicking up at different rates. And I can tell you from this parametrization where you are on the curve. So this is a reparametrization, because now my sigma, which was originally sigma of t, is now sigma of t, which actually maps directly to s. So sigma of s. And we'll just use the chain rule to argue that at the very least, the direction of the tangent hasn't, the direction of the curve of the tangent doesn't change. So we use the chain rule. We all enjoy the chain rule. Everyone's having a good time with it in their assignment, I imagine. X of t of s, y of t of s, z of t of s. Okay, expand these out. It's all single variable, so there's not even anything particularly difficult to do here. T dashed of s, y dashed of t dashed of, y dashed of t of s, t dashed of s, z dashed of t of s, t dashed of s. Let's pretend I gave myself more room. So much foresight. Which is equal to, well, remember, it's just a vector, so you can factor out the t dashed of s times by x dashed of t of s, y dashed of t of s, z dashed of t of s. And you can see something that sort of intuitively makes sense based on what I was saying, which is that the direction is exactly the same as the direction of the vector parametrized in t. But the magnitude has scaled by t dashed s. So the magnitude of the derivative changes when you express it in a different parametrized coordinate, but the direction does not. And that makes sense because, like, I don't need to know t to draw the direction, but I absolutely need to know t to be able to figure out the magnitude. So it makes sense that one of those things would be preserved. Okay, so that's nice. Let's imagine a nice easy one. Let's say I said t of s is equal to s over 2. Easy reparameterization. I'm just saying, all right, it's going half as fast. So I would hope that my derivative would point the same way, but be half the size. So now I'm moving from s equals 0 to s equals 2, and my d sigma ds is equal to t dashed of s d sigma dt. And t dashed of s is nothing more than a half d sigma dt. So it makes sense, right? Like, this is, we've parametrized it so it takes twice as much s to get anywhere, which means as I vary s, it's traveling half as fast. I'm using fast in a slightly loose sense because it helps convey an idea of what's going on dynamically. But there is no speed per se. It's a derivative which can measure speed if you think of the parameters as indexing progress. If that helps you, hold on to that way of thinking about this. It's how most of us actually deep down think about this stuff. But if you don't, you can get away with symbol pushing here and you won't have too many problems. So if it helps you think about it, that's good. And if it doesn't help you think about it, that's okay. You're not required to think about it that way. Okay. So a useful reparameterization is, as we learned, S of t is the arc length from A to t, which means if I have my curve here and I have some point t, then if I calculate this length to be s, probably this is a very sensible way to parameterize this curve. And of course it's a sensible way to parameterize this curve. So let's calculate it out and see what it means. S is equal to the integral from A to t of the square root of x dashed, and we have some dummy variable. I'm going to call it r, but if I was in the assignment, maybe I would have called it t dashed. I don't know. If you're struggling with dummy variables. Squared plus y dash squared plus z dashed of r squared dr, which, as we discussed, is simply the integral of the norm of the vector, of the derivative, dr. Okay, so we take the derivative, get to use the fundamental theorem of calculus, which is always fun. ds dt is equal to the derivative of this thing with respect to t, which is what? Hand up. Wake up. Derivative of that with respect to t. We are not moving until someone gives me... Yes? Exactly. What's inside evaluated at t. Thank you. So we get... I know you know that. I hope you know that. I know you have in the past known that. You should know that in the present as well. ds dt is, of course, the integrand evaluated at t. Fundamental theorem of calculus. Okay, so this has a very useful property, and it's a property that will allow us to define an integral along a curve without actually getting too stressed about parameterizations. So if I take d sigma ds, then just using the chain rule, I can get sigma dashed of t of s times by, because it's the chain rule, dt ds. Now, I have a little side note here. You might think, and you would be right, that it is reasonable to say that that is 1 over ds dt, because it's a total derivative. But we probably shouldn't take anything for granted, because we are now working in a slightly different integral context because we're tracing out curves. So just on the side, just to make sure everybody is happy with this, a little derivation of the total derivative rule to show that nothing breaks because we're looking in this slightly different context. So this operation is still valid. I didn't want to get sidetracked on it, but I just wanted to include that in case anybody was worried, because it would actually be quite a legitimate worry. So we can still say that this is 1 over ds dt. But we know ds dt. Well, more or less. So what we have is sigma dashed of t of s, why not, over the norm of sigma dashed of t of s, and that is a very useful kind of vector. Tell your friend why that is useful. Hands up if your friend told you that it's a unit vector. Good. Good. Yeah, exactly right. What that means is that the norm of the derivative is the norm of sigma dashed of t of s over the norm of sigma dashed of t of s, which is equal to 1. Arc length parameterization is constant speed. As s changes, the length changes by a constant amount. Intuitively, this makes sense if you think about it, but intuitively this makes sense doesn't get to have a little box in the corner. So we're doing things at least a little more carefully than that. But the way we pick the definitions and things is picked so that this works like you think it should. Now, of course, this is if you're sort of like, so one of the problems is when you actually need to evaluate an integral, probably you need to sit down and construct a parameterization. Talking about these things in general is nice, but in life, every now and then, when every alternative has failed, you actually need to do an integral. And when you run out of other options and have to do the integral, then you do have to, even though parameterization is essentially unimportant, you still have to pick one. And if in doubt, picking arc length as your parameterization variable generally causes you the least problems. Okay, but everything up to this point, kind of revision, right? In fact, this is a really good place to take a 30-second break. So do that, and I'm going to make sure I know what I'm about to teach you because it's been a busy week. Take 30 seconds. All right, good, good. Okay. So I got into work this morning and the printer wasn't working, which means all I could do was pull up my notes on my phone, which is about this big, which is probably the worst possible way of doing it. So I have my computer notes here, but I also can't see how thick my notes are, so I have to check how long I have left. We have heaps of time today. The plan for today is actually for the new stuff to take up the first hour and a half, and then for me to fill up the end with more multiple integrals just to keep you entertained. So we're not rushing today. But I didn't want to spend too long on this because this was kind of revision-ish. Now we're going to generalize into something quite important. So here, I said, this takes a single variable and spits out multiple variables. And here I said this takes multiple variables and spits out one number. But there's no reason for things to, for one side or the other to have to be one number, right? We can take in a vector and we can spit out a different vector. The vectors don't have to be the same size by any stretch of the imagination. And by doing that, we come to a new construction, a construction which maybe you've considered and maybe you've sort of brushed past in passing without realizing that it was quite a complicated object. We're going to talk about vector fields. So we've been integrating a constant value along a curve, but now we're going to talk about vector fields as an object. So we're going to let my vector field be f of x, y. A quick note about underlines. I am trying very hard to remember to always underline vectors, but once we start to have a lot of things flying around, it's possible that they may start to get omitted. I will hopefully explicitly flag when this happens, but get used to now working out from the context of the question what an object should be. I will try and keep this flagged, but mathematicians are rarely so careful about this. I apologize for my people. So, got a vector field, and what it does is it spits out a vector. So it takes in a vector, and it spits out a vector. No great surprise, we've been working with the chain rule. We understand what that sort of thing means, but now we're going to start doing calculus on it. Vector-valued functions of a vector-valued input. Rm to Rn with no restriction that m and m should be the same. At each point xy, so a way this often gets visualized, and this is a very helpful visualization, but it is just a visualization, so don't use it too much as a crutch. At each point xy, there is an arrow or vector given by the vector f1 of xy, f2 of xy. So you're used to seeing things where, you know, z of xy is equal to 3. But now it's a vector. So at each point in the plane, the output is some vector, which has its own magnitude and direction. And you shouldn't think of these vectors as being embedded at these points. That's where this starts to create a slight misapprehension. These are just vectors. Okay? If you pick this point xy, then the output is this arrow. The input is a vector, the output is a vector. These are not, the output vectors are not like embedded at this point. That's the mistake people make, and that's the thing I want to stress, is that it is just a vector associated with that point. It is the vector that is the output of the function. But we draw it this way, and this is a good way to draw it. It is a particularly useful way to understand many of the common vector fields you will meet. If you're in physics, you will meet electric fields, you'll meet gravitational fields, you'll meet magnetic fields. If you're in mathematics, you'll meet differential equation fields, which we will talk about a bit in the second half of the semester. This is a really useful tool, but you need to use it for calculus. So at each point, this is, if this is x naught, y naught, then the output is f of x naught, y naught. This is the object that will be the rest of the vector calculus subject, so we're going to get quite comfortable with working with these, and we're going to talk a bit about what they mean. But we're going to start by sketching a vector field. It's an example, and again, it's an example that we're going to sketch the arrows in the position. So my vector field is minus y and x. I'm going to do 1, and then I'm going to get you guys to actually fiddle with it for a few minutes. So I'm going to say what this vector field looks like at 2, 1. So at 2, 1, f of 2, 1 is equal to minus y, so minus 1, and x, so 2. So minus 1 across and 2 up. So let's just move this out of the way and say that my vector looks like this. So at the point 2, 1, I sped out an arrow that's going left and up and twice as up as it is left. I would like you now to do a couple of these to get a feeling for drawing this yourself. So take a moment and draw out maybe one in each quadrant or even a couple. And see if you can get a feel for what this vector field looks like. We will learn how to visualize these on computer. Visualizing vector fields is a really useful thing to do in Mathematica, and is one of the reasons why Mathematica was sort of targeted at this subject as a place to learn how to use it, because vector fields can get very complicated. If you're watching at home, pause the video and fill out the whole thing. That's the price you pay. And my absolute favorite thing about teaching this is watching about 7 people in the audience at any given time figuring it out with their hands. Amazing. Do that. Fantastic. Whatever gets you there. All right, I have given you a bit of time and hopefully you've sort of kicked around these ideas a bit, but while you were doing that, I was filling in the picture myself. And you can see what's happening is the vector field is in some sense swirling around the origin. So it is in some sense swirling around the origin. You might even imagine that if this could be thought of as, say, a current, there are trajectories that might connect up, and that is in fact something that we will find. So this is quite a useful vector field in many ways. If this was like a whirlpool and I dropped a cork here, it would swing up and around and down and across. It wouldn't always be at the same speed because, of course, this has a bigger magnitude, √2, than this, which is 1. So it's sort of swinging around like this, but it is, well, it's actually following circular trajectories, but whatever, we're trying our best. The point being that the vector field takes a point in space and returns an arrow. And that arrow tells us something about what we are trying to understand. So one thing we want to do now is we've taken this quantity, this line integral, and we want to say, well, what about if the quantity we're trying to integrate along the line is not just a function of t that produces one variable, but rather a vector field? And this is why you meet line integrals about 20 minutes before you meet vector fields, because this is such an important, this is the reason, this is the most important thing you can do, I would say. The path or line integral of a vector field f along a curve sigma t is defined as the integral from a to b in terms of some parameterized variable t of the vector field evaluated on the curve dotted with the derivative of the curve. So would it shock you to know that there's some linear algebra here? this is a definition, but it is a very useful definition. We're at the point where we can define a trillion different things, and half the game is finding definitions that are useful. This is an incredibly useful definition, and that's why we learn it. So, what does it mean? Because like vectors, integrals up until now have been relatively easy to look at and interpret, and I think you are all quite good at understanding what they mean. But there's a lot going on in this integrand. The integrand has a dot product and a derivative, and there's all kinds of stuff in there. So let's pick it apart and see what it is. And to understand what this is, we need to remember a very basic fact from linear algebra, which is that u dot v is the amount of vector v acting in the direction, amount of vector u acting in the direction of vector v. It's the projection of u onto v, which is to say that we are doing some kind of projection. Projection of u onto v, up to scaling. The amount of vector u acting in the direction of v. Our integrand, if we interpret it this way, is the amount of f which is in the direction of sigma dashed. But the direction of sigma dashed is very important. We've already talked about this. There is a reason it's defined this way. Sigma dashed is parallel to the curve. So think of the direction of sigma dash as being the direction of the curve. And what we have here is the direction of the curve at t. So if my vector field here goes like this, say. So here is my f of x of t, y of t. Then, of course, there's some angle between them. And that angle may be 0, it may be pi on 2, it may be something else entirely. Then the projection of f onto sigma dashed, which is to say the projection of f onto the direction of my curve, is equal to, we all go back to first year, and we write sigma norm times the norm of the second thing, times by cos of the angle between them. So here, this is just a path scale factor. It's almost like we might come up with a particular parameterization that makes that 1. I'm sure you might be able to think of what that will be. And this is the amount of f in the direction of sigma of t. So this is fine for some people, but when you meet this for the first time, it's nice to see a bit of a hand-wavy example. The next few slides are not rigorous, but it is an explanation which for a lot of people makes sense. It ties it into something you can imagine. So this is a very common analogy given the first time you meet vector fields, is imagine a river. It looks like that. The physical intuition for this definition is that the line integral is a measure of work, the amount of work done by a vector field in the direction of the path. For example, if I have my flow and it's all flowing downstream and it's all going at a constant rate and life is very easy, and I want to cross the river, I'm going to say there are 2 ways I could do it. The first way I might cross the river is path number 1. That is the other end, and I'm going to cross it. The second way I might cross the river is path number 2, which is to say, like, I'm happy to kind of dilly-dally a bit downstream. So I've picked 2 paths. These paths are their own thing. They are nothing to do with the field. They are just the direction I'm choosing to go. Now, if I follow path 1, at every point on the path, the field is acting perpendicular to the path, which means at every point on that path, f dotted with sigma dashed is going to be 0. So at every point on that path, f of xy, f of sigma, dotted with sigma dashed of t is equal to 0, because they are always perpendicular to each other. But here it's not the case. Here, I'm getting a bit of a push from the field in the direction I want to go, which means the field is doing some work in the direction of the prescribed curve. That is what this integral is measuring. What that quantity can mean can get abstractified a bit, but broadly speaking, this is an intuition you can have in the back of your mind, and it will generally not let you down. But of course, this is math and not fluids, so we're going to actually calculate these out, because why would I make your life easy when I can make it hard? Let's imagine that we have our river, we have our paths, and I've got this vector field here. And what I'm saying is that, all right, between y is 0 and y equals 1, at the edge of the river, the flow's not moving. But as I get to the middle of the river, where it's deeper, it's got more room to go, the current is faster. So the speed of the current is maximal in the middle of the river and 0 on the edges. Let's actually evaluate the corresponding line integral. To do the line integral, as I mentioned, when you actually sit down and evaluate one of these, even though parameterization doesn't really matter, you still have to sit down and work out a parameterization. So we're going to say sigma 1 is a map from 0 to 1 to S, where S is the value. And what I'm going to say is sigma 1 of t is equal to 0t. Okay? S, yeah. S is our region that we're interested in. I was like, that's not what S is. S is a parameterization. S is a point on our curve. So this maps from 0 to 1 to a point on our curve. Sigma 2, I'm going to give a different map to a point on the curve where sigma 2 of t is equal to 2t t. So S is our whole region on which we are describing our vector field. And these are our paths within the region. So our first path, x is always 0, and y varies from 0 to 1. Our second path, y varies from 0 to 1, but x varies from 0 to 2. So here we are going from 0, 0 to 0, 1. And on our second path, we are going from 0, 0 to 2, 1. And because of the form of the parameterization, I think it is clearly a straight line. I don't like to say clearly, but this one should be pretty clear. Okay, and now we actually do the calculation. So the is equal to the integral from 0 to 1 of f of sigma 1. So that is going to be y of t minus y of t squared, 0, dotted with sigma 1 dashed, which is nothing more than 0, 1 dt. So I've pulled this y minus y squared in my f. Let me finish what I'm saying, and then I'll do that. And this should be the derivative of this with respect to t. Yes? It absolutely is supposed to be y between 0 and 1. The good news is I got that wrong on my notes. I saw it correctly. I just wrote it wrong beforehand. Thank you. I appreciate that. Good. So now we do this. But we have y of t, and we're going to need to get that from somewhere. Fortunately, we know what y of t is. So our y of t is going to be nothing more than t. So this is equal to the integral from 0 to 1 of t minus t squared 0, dotted with 0, 1, which is equal to the integral from 0 to 1 of 0 dt. It's a terrible 0, which is 0. Okay, so we're in pretty good shape. That is exactly what I hand-wavingly told you it should be. Let's see if the second thing is what I hand-wavingly told you it should be, and then I'm going to give you a long break. So stick with me, guys. We are almost there. F doesn't change. F is still y of t minus y of t squared and 0 dotted with, but now this does change, because now we're looking at this. Blue is already used on this page. Now we're looking at this, and its derivative is going to be 2, 1 dt. And you can see these two vectors were perpendicular to each other, so it was pretty obvious that they were going to be 0, and you can sort of see why if the field is always orthogonal to the curve, it must always be 0. And you can see here these won't be orthogonal to each other, so they will, in fact, hopefully, give us a non-zero answer. 0, 1. Y hasn't changed. It's still t minus t squared 0, but now this is 2, 1 dt, which is equal to the integral from 0 to 1 of 2 t minus t squared dt, which I'm reliably informed from my calculations before is 1/3. So f acts in the direction of this curve. It does not act in the direction of this curve, and thus the line integral of this curve is not 0, and here it is 0. One of the reasons for doing such a simple constructed example is to help you develop some intuition for what this integral means, because this seems pretty straightforward here, but it's going to get a bit more complicated when we have to start imagining more and seeing less. Take, let's say, 8 minutes, and then we will finish this off. Probably I won't do a bunch of extra multiple integrals at the end, because we're going at a fairly measured pace today. Also, I love that you ask me questions sometimes, but at least give me a minute before you do.
too long. And I
That's okay. I've had my moment.
I get what he's saying. I'm just asking, like, why is this unusual? Because, like, why do we exclude perpendicular?
Because
I get the work analogy, but, like, as you said, this is not fluid, this is maths.
yeah, you're right. So we will want to know about vectors acting in directions along surfaces and perpendicular to surfaces. Eventually, a thing that we like to study is flow on surfaces. You might have heard of Ricci flow. That is a flow on a surface.
No.
Okay. Yeah. So think of these as a way of studying flow, and think of this as a way of restricting flow to a surface, and then like that is obviously quite applied, but it's very differential geometry because it starts treating the surface as the inherent object again.
Yeah, so we're looking at what I was thinking is we're kind of looking at, like, another way to think of it is we're looking at, like, how similar this oriented, like, vector line is to the vector field.
Yeah, think of it as decomposing. Decompositions are an important part of mathematics. And you can think of this as decomposing the action of the field, and action is a purely mathematical concept. The action of a field in the direction of a surface versus the action of a field perpendicular to the surface.
Yeah, I'm just thinking is because before when we're looking at multiple integrals, we're looking at, like, the total, like, accumulation of some function over a region, right?
Yep.
And like I was thinking, okay, with the kind of vector equivalent, we look at the accumulation of a vector over a region.
We will do vector integrals soon, but
this is different from the line integral because, like,
the line. Great question. In a very real sense, there is no difference at all. But, well, no, in a very real sense, they're tied together. We're going to meet Stokes' theorem and the divergence theorem, and what that will end up doing is tying together things like line integrals, surface integrals, volume integrals, one kind of Uber structure.
Yeah, I've heard of that. I'm just sort of trying to understand more.
Yeah. We are, in a sense, we are, but we've been doing this with integrals more generally. Anytime you integrate against a kernel, anytime you integrate against a distribution, you are integrating against something. In some sense, we're integrating against a vector field. So, I mean that we are thinking about what some quantity is doing in the region rather than just like adding stuff up. That's a bit wishy-washy.
Yeah.
If you want to keep it sort of tight and mathematical, think of it in terms of the language of decomposition. But a little bit of physical intuition goes a long way.
We're looking at, like, to what degree it's parallel to the field, basically. We're looking at the parallel component of this.
That is a helpful way to think of it, yes.
And I guess theoretically, we could look at the perpendicular components if we did, like, the projection.
We later on will learn about, well, in this subject you won't, but, well, in this subject, hold your horses. There's an answer to that question. All right, I have exactly 8 minutes, so let's get back in. Let's do another example. Let's do water flowing along a stream. It's a good example. But what I'm going to do is I'm going to emphasize I picked the two easiest curves that I possibly could because they are easy. One doesn't have to pick easy curves. You can imagine parameterizing curves in very complicated ways. You can imagine, as we learned in the seminar last week, that thing we did to generate the knot, which was just tracing a curve around a torus, that's just a parameterization. You can integrate along it. You can integrate along all manner of very complicated curves. So, in the interest of I don't want to do something too complicated, we're going to integrate along quadratics. But they don't need to be lines. They don't even need to be acting in the direction of the field. So I'm going to say my first one is I jut out, and then I'm like, oh, the current's a bit deep. I'm going to pivot back. So here is my curve number 3. And curve number 4 is someone who watched number 3 and was like, no, 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 not making that mistake, and goes the other way, fights the current. We've developed a little bit of intuition here. we might expect that f is acting some part in the direction of curve 3, because curve 3 wants to go a bit downstream, and the field is helping it. But number 4, we want to go back upstream. We're fighting the field. So we might expect that our integral is going to wind up being negative. And sure enough, if I do my math right, that's what we'll find. So there is a 50-50 chance that that is what we will find. So we'll parameterize our curves. And in this case, I'm essentially giving you the parameterization. I'm saying that between 0 and 1, we map onto S. And our curve is defined as x is t, but y is t squared. So t is ripping up there much faster. And sigma 2, 0 to 1 of S, sigma 2 is minus t to t squared. So they're both moving vertically at the same pace, but one's going to the left and one is going to the right. Okay, so we'll evaluate that just to shake off the rust a bit. Integral from 0 to 1, and we pull f from above. It's just y of t minus y of t squared. And this is still 0 because I want the calculations to be one line. Dotted with sigma 1 dashed. So that is going to be 1, 2t dt, which is equal to the integral from 0 to 1 of t minus t squared, 0, dotted with 1, 2t dt, which is the integral from 0 to 1 of t minus t squared dt, which is a number that I didn't write down. Good job. Oh, yeah, right. Apologize. This is the whole point of the question. Good. Y is in fact t squared. So this is t squared minus t to the 4. Good. All right. Now we're back. Integral from t squared minus t to the 4 dt. And the answer is whatever that is, but it's going to be positive. Whereas if we go the other way, integral from 0 to 1, y of t minus y of t all squared 0, dotted with, now we get minus 1, 2t dt, which is the integral from 0 to 1. Again, our y hasn't changed, so it is still t squared minus t to the 4, 0. The thing that has changed is this minus 1, where there was a plus 1 before. Minus 1, 2t dt, which is, of course, minus the integral from 0 to 1, t squared minus t to the 4 dt. So you can see here exactly the opposites, which rather makes sense, because the field doesn't change in x. So by going to the right, it's exactly the opposite as going to the left. In general, you wouldn't necessarily, for an arbitrary field, expect that these have to be negatives of each other just because we flipped one direction. You might expect there are quantities that will negate other quantities, possibly traveling in the opposite direction along the same curve, but we will get to that at a later stage. So, a quick final note about this. Path integrals can be negative. If the field opposes the curve curve direction. Good. Good. Okay. So those are some fairly sort of constructed examples. Let's go back to that field I drew before. So here is the field I drew before, f minus yx. And the curve I want to calculate is along the curve parameterized cosh t and sinh t from t equals 0 to t equals t. when you have a parameterization you can draw, you should draw it. Just to know, just to get an intuition for what's going on. So here I've got my x of t is equal to cosh of t, which for later use means my x dashed of t will be sinh of t. And I've got my y of t is sinh of t. And for later use, my y dashed of t will be cosh of t. An even easier thing than sines and coses. So when t is 0, cosh is 1 and sinh is 0, so I start here. Let's do this not in red. So when t is 0, I start here. And then, as t increases, cosh becomes more positive, sinh becomes more positive. We probably look something like that. In fact, we look exactly like that. But, you know, maybe we don't know that. Okay, so here I have sigma of t. So more or less, it looks like the field is helping us move vertically, but it's not so hot on us moving to the right. Which is to say, some of this field will be acting in the direction that our curve is traveling, and some of this field will be acting in a direction opposed to the way in which this curve is traveling. And it's not totally clear what even the sign of our answer will be. When in doubt, crunch the numbers. It's not the fun part, but this is got to crunch the numbers in this subject sometimes. Okay, so the integral from 0 to capital T of minus y of t, x of t, because here is our field, dotted with, okay, so we need sigma dashed, so that's going to be x dashed of t, y dashed of t, dt, which is equal to the integral from 0 to t of minus sinh of t, cosh of t, dotted with sinh of t, cosh of t. And we go to our hyperbolic tables, and we're like, oh, wow, that's a special identity. Cosh squared minus sinh squared is nothing more than 1. So that's the integral from 0 to t of 1 dt, which is equal to t. So there is an interesting point I would like to make here. Aside from the fact that we just did a calculation and it worked and that's nice and the answer is t, good job, is that this point here, 1, 0, at this point, the field and the curve are both going in the same direction. The angle between them is 0. So that means that we are in fact, at this point, and no others, but at this point, the field is acting entirely parallel to the curve we are interested in. This can happen. Sometimes it is good to know that. What it means is that, in the language of before, all of f is contributing to the path integral. The projection of f onto the curve is f at that point. So in terms of, sorry, I should have actually put the coordinates in rather than just talking about them. F of minus yx is equal to 0, 1, and sigma dashed of t is equal to 0, 1, i.e. they are parallel. We talked about what happens when they're perpendicular, which is to say you get no contribution. We talked about what happens when they're parallel. You get the whole thing acting in the direction of the curve. Okay. Do I ever get tired of examples? One more example. But, you know, they're getting a bit harder to visualize now. So, sort of, we were able to hazard a bit of a guess as to what was going to happen by looking at the field. But here, like, your guess is as good as mine, probably. The only reason that I can guess this any better than you is I have the answer in front of me. Which is to say, I've got a vector field, and it's the helix from last week. So x is cos of t, y is sine of t, and z is t. So we're spiraling up the real axis, the z-axis. My field is x, y, z. What that means is at the origin, my field is 0, output 0. But the further I get from the origin, the more powerful the field is. So you can sort of imagine as I spiral up here, that field is going to get stronger and stronger and have more and more of an effect. And that is true. But we're just going to calculate it for one full rotation. So t goes from 0 to 2 pi, which hopefully means it goes from here to here. Okay. And aside from the setup, same ball game. Okay. So we've got the integral from 0 to 2 pi of our field f evaluated on our curve, projected onto the direction perpendicular to the curve. So f is going to be x of t, y of t, z of t, which is equal to cos of t is our x, sine of t is our y, and t is our z. So, putting this together, and not wasting too much more time, cos of t, sine of t, and t, dotted with sigma dashed. Okay, so sigma dashed is going to be, derivative of cos is negative sine, derivative of sine is cos, and derivative of t, thank you, minus sine. See, this class is easier when you guys teach it. Minus sine of t, cos of t, 1 dt. And now, algebra, 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 minus cos of t, sine of t, plus sine of t, cos of t, plus t dt is equal to, now this is interesting. And it's possibly something that if we had a few extra tools, we might have been able to predict. Which is to say, nothing in the rotation really matters. And when you think about it, and you think about this field, it makes sense. Because everywhere I am in the rotation, the x and y is pointing perpendicular. The x and y part of the field is radial, which means it does not matter where I am in x and y. As long as I'm following these constant curves of constant radius, then the field will always be acting in the xy plane perpendicular to my curve, and the only thing that will matter is the z plane. So I was pulling the wool over your eyes a little bit when I said actually we can't tell what's going on, because there is some intuition we can apply to this once we start to get a hang of these. And this brings me to a really important point which probably won't make everybody happy, which is that we are basically going to stick to R2 and R3 now, but for good reason. Because we are about to start to think about differential operators in R2 and R3, and those get, every dimension you add makes those infinitely more complicated, and there are certain differential operations that will not generalize. So the standard vector calculus approach is to really get a handle on R3, so that in third year, we can teach you what these concepts are in higher dimensions. So we are now, if I give you a problem, assume it is in R3 unless I very explicitly tell you otherwise. It's going to become apparent why we need this in, I'm going to say, one slide. So this is important. Because we're working on vector fields, we have a whole array of new options for operations. We're actually learning new operations now. Last time you did this might have been when you learned to integrate. We're going to make use of new operations, and we're going to build them out of things that we know, but they're things that only make sense in terms of vector fields. And let's think about a couple of these fields and talk about why they might be inherently different to each other. So look here, this field swirls around, doesn't really spread out. If I drop a cork here, it's just going to float around the middle, not going anywhere, just spinning around. But here, this field is very different. If I drop a cork here, it's going to shoot off and get as far away from the origin as it can. It's spreading out. Spreading out and swirling are the two basic things a field can do in R3. And this is going to be quite important. So we're going to start by talking about the divergence of a vector field. You might, if you're a keen student of the English language, consider that divergence might refer to how much a field spreads out. And that is true. That is exactly what the divergence measures. So the divergence of a vector field is denoted grad.f, or if you like, div of f, mostly if you're a 19th century electromagnetism person. Grad.f. This works fine. In 2D, if my field is PQ, then grad.f is equal to px plus qy. In R3, grad.f is equal to px plus qy plus rz. The extension to Rn for the divergence is very, very obvious. I think you can figure it out. We know what gradients look like. But we're going to focus on R3 and R2, but that's just an easy version of R3. So you might think, okay, cool, so this is how total derivatives work in higher dimensions. That's nice. But this doesn't tell us everything about a field. This tells us a lot about what's going on here. If you calculate this out, it'll tell us that these are going to get bigger and bigger and bigger the further away you go. It's going to tell us how this field is spreading out. But it isn't going to tell us anything about this field. And you can calculate that yourself. You can see that the divergence of this is 0. So this is no longer, the total derivative in one dimensions is able to encapsulate all of the variation that a function can do. But no single differential type operator is now capable of capturing everything that a vector field can do. So we need more than one. And as you can imagine, that is going to make the fundamental theorem of calculus, when we get to it, a nightmare. But actually amazing. So let's talk about divergence. Divergence measures the spread of a vector field, and we're going to put some precision around this next week. This is kind of an introduction to next week. So if I take this field here, x, y, 2 dimensions, everything is moving outwards from the origin, then what you can see is that grad.f is equal to 2. And in some sense, what's going to happen is if I put in a drop of colored dye and let that dye evolve, then the dye would spread out and the area that that dye covered would get bigger. So the divergence is actually telling us that the actual area is spreading out under this field as an operation. So if the divergence is positive, it is spreading out. And if the divergence is negative, it is compressing in. This is almost easier to imagine if you imagine all the arrows pointing in. If I put a circle here and trace those points, it's going to get smaller and smaller until it collapses to a point. So the divergence. But if I take that one from before, or a variant of it, I put the minus so it swells in the other direction. F is y minus x, then if I calculate this, it's 0. Is this doing nothing? Not really. It's kind of just rotating. If I put in my circle here and just leave it be, the circle's just going to go round. And then it's never going to grow, it's never going to shrink, it's going to be the same size. Question? Sorry? No, not necessarily, not at all. We're going to see some weird things. Don't try and read too much into that. It just means that it's not spreading out or compressing. It can be 0 at points and non-zero at other points. This is a function. I just happened to pick some numbers which made them constants. Yes?
Is it nice to get divergence around like that?
Is it?
Imagine I wanted the divergence around 2, 2.
Oh, yeah, but you can always do a translation. Yeah. We will make use of that to prove something later on, I think. Good instincts. Okay, so that is divergence. For now, I'm telling you this is an intelligent thing to calculate. Next week, we're going to see where it comes from naturally. But I want you guys to have met these today. I even tweaked around a lot of things to make that happen. Now, there is nothing about this that doesn't work in R4, R5, whatever dimensions you want to do, as far as your imagination can take you. However, if I want to start talking about something like this, that's where things get complicated. The second kind of vector operation we might want to talk about is the curl. You've met the dot product. Does it surprise you that the cross product is also a relevant operation here? Now, the curl is defined in a slightly... I'm going to give you the 3D definition because that is the right definition, and then we're going to talk about the slightly degenerate 2D definition. So, in 3D, the curl is Ry minus Qz, Pz minus Rx, Qx minus Py. It is exactly what the cross product operator tells you this should be. Remember, this thing is essentially partial partial x, partial partial y, partial partial z, crossed with F1, F2, PQR. PQR. Okay, so it gives us this quantity, and this quantity is a vector. Now, the fact that we are using the cross product to define it is why we are stuck in 3 dimensions. There are generalizations to higher dimensions. They are difficult to interpret geometrically, almost impossible to interpret intuitionistically until you put in a lot of time. But later on, you will meet things called exterior and interior derivatives, which is the higher dimensional generalization of this. We do not have time in the next 2.5 weeks to get anywhere near that, but in 3rd year, that is something you will hopefully see. Okay, so it is a vector quantity, and it is that, and I'm telling you it is that, and we'll talk about what it measures in a moment. In 2D, we call it the scalar curl, and it is just Qx minus Py. So we actually call this scalar curl just to be a bit careful. And it is nothing more than what the 3D one would have been if the field is Z independent and the 3rd entry is 0. So this is essentially, it doesn't even have to be Z 0, but generally that's how we sort of talk about it. So this is essentially this entry, and if you imagine that R is 0 and Q is 0, then it's actually what the 3D curl would be. Mostly in 2D, you calculate this, and in 3D, you calculate this, and if I don't give you any advice on which of those two, then this is always solid. So the curl, you might think, that is a weird definition, but we'll just roll with it for now. Again, you're going to learn why this definition is helpful down the track. Curl can be defined in higher dimensions, but it is not straightforward, and it is not as geometrically obvious what it means. I've said it's less meaningful. I think that might be a bit pejorative. Let's say the meaning is less obvious. A useful way to remember the curl formula is to write it as a determinant. It is not a determinant, but through what can only be described as magic, the formulas come out right. So remember, these are the unit vectors in x, in y, and in z. So we get I, Ry. I was a PhD student before it really clicked that this was not a determinant, so that's not quite as obvious a thing as it sounds. Pz plus k Qx minus Py, which is equal to Ry minus Qz, Pz minus Rx, Qx minus Py. And this is why you should never memorize the formula for the curl. You should just know this. It's not a determinant, but it behaves like one in every meaningful way. So, good. That's how you should probably remember it. Okay. We understood what the divergence meant. It meant how it was spreading out. And in 2D, it's sort of obvious what it means as well, because we get a number. And that number is a measure of how swirly it is, which is to say how much work is being done by F in a rotational direction. Important point. In 2D, rotational directions and radial directions actually have a very important significance that extends beyond this is what they do on the plane. If something is moving radially, then its direction, then essentially its acceleration is in the direction that it's moving. If something is moving radially, then its velocity is perpendicular to the direction that it's moving. Just kind of like orbital mechanics if you did them in grade 11. But this is breaking it down to just directions of curves. So we talked about what it meant for the projection of F to be on the direction of a curve. Here, if you are moving radially, then F is acting in the direction of your curve, and if you are moving axially, then F is going to be perpendicular to your curve. Generally speaking, if you move freely in these fields. So you don't really have to take that home. The thing to sort of remember is these are very canonical constructions. This is to do with moving parallel to a field, and this is to do with moving perpendicular to a field. So these are not just like these are the two shapes we decided to measure. These are the natural ways to characterize a curve in 2 and 3, to characterize a field in 2 and 3 dimensions. And if you see something that looks like this, if you go back and calculate this, you get that the curl of F is equal to 0. But if I have this curve from before, then I find that the curl of F is not 0. But curl is a vector, or at least in 3D it is. So there's more information. If we just look at the size of the curl, we're throwing stuff away. There's another piece of information about the curl that is very important that we use, and that is its direction. So the magnitude tells us how much swirl we have, but the direction tells us something as well. The direction tells us that if we just think about the swirly stuff, it's going to have an axis. And that is what the direction of F tells us, of curl F. So the direction of curl F is giving us more information. Going back to our interpretation in 2D, this is kind of telling you that if the curl in 3D is 0, 0, this, then its direction is the z direction. So that says that the axis of rotation is the z direction, and the rotation is in x and y, and that is exactly what we see. So this interpretation makes a little more sense once you understand what the direction of this vector is trying to tell you, which is what is the axis of rotation. Okay, here, of course, curl of F is not the 0 vector. How much work is being done in a rotational or axial direction? And, of course, what is the axis, which in 3D is very important. If you just measure the swirl, you're throwing away free information. This is why, in general, when you go to higher dimensions, and again, I don't want to dwell on this, the divergence stays as a scalar derivative, and the curl is one dimension short of the space you're in, because that extra dimension, that tells you about your direction of your rotation. But again, we're not doing that. You're not going to meet that in this course. I will briefly, I think, at the end of week 6, introduce kind of historically how this happened, but we'll get to that later. Okay. Divergence is typically a very easy concept, and curl typically trips people up a bit. And a way, if you have quite sort of a kinetic mathematical imagination, imagine placing a water wheel in our flow field. If I have my first field, which has curl but no divergence, then here it is quite happy just to be spun in this direction. Yes?
Does the curl represent like the torque?
Sorry? That's a little physical.
Or is it linked? So is the curl at least the direction of rotation the same way torque? Like,
Yeah. the direction of the curl is the direction of the axis of rotation of the field, of the rotational part of the field. We will learn later on that, at least in 3D, you'll be able to decompose curves into the spread part and the rotating part, and the axis of rotation of the rotational part of the decomposition. Like I said, a lot of the concepts that I'm introducing a little sort of hand-wavy today, we're going to introduce very carefully through the lens of vector calculus next week. I just wanted you to meet them first before you meet them dressed up in a tuxedo. So, the second vector field has zero curl, and you can see this is pushing it this way, and this is pushing it this way. So you might imagine it wants to spin like that. But this is pushing it to the left, and this is pushing it to the right, which means they're kind of undoing each other. And these two are kind of undoing each other. And our water wheel is just going to sit there. This field is curl-free. So in this case, if I actually calculate these out, grad cross f is equal to qx minus py, which is equal to 2. So the wheel spins. Grad cross f is equal to qx minus py is equal to 0. The wheel does not spin. But there is something interesting here. Well, I think it's interesting. You can think what you want. I've got the microphone. Which is to say, in general, there's no reason for these to be constant other than the fact that I picked very easy fields. What this is telling me is it actually doesn't matter where I drop it, the wheel is going to spin. So that's a bit, it's kind of obvious when I put it in the middle, but it's a bit less obvious when I put it here. Why is this water wheel going to spin? The top is moving clockwise, the bottom is moving clockwise. Surely those things should repel each other. But look at the size of the arrows. Here, the inside arrow is very small and the outside arrow is bigger, which means that those forces don't cancel. There's some leftover force on top that is going to cause the wheel to keep spinning. So the size of the vectors becomes important. And this is why even when you look at a picture, it is not, this intuition will eventually let you down. That is why you probably do want to do these calculations. You should have an idea of what a rotational field and a divergent field look like, and by God, at the end of next week, you will have an idea of what those look like. But a bit of intuition helps. Don't use it to replace the actual calculations here. It's really important. Okay. A question to leave you with before I go and do a few tedious multiple integrals. I kind of want to take you back to parametrization, and there was an important idea we talked about, which is that a curve can be represented in multiple ways. So I could say, all right, I'm going to start at t equals 0. I'm going to slide down my rope to t equals 1. So a nice sensible parametrization is x is equal to t, y is equal to 1 minus t, which takes t is 0 to 1. Now in all of the other parametrizations we saw, we changed the parametrization, s over 2, we changed some numbers. Try this one on for size. X is equal to sine squared of t over pi. Y is equal to cos squared t over pi. Well, in fact, if I do that, I'm going to start here, and I'm going to slide down here, and I'm going to end at t equals 1. But I'm going to get there in a very different way. An exercise I would like to leave you with is, can different parametrizations change the value of the line integral? Gut instinct here. Hands up. Everyone's got to vote. Don't care if you're wrong. Hands up who thinks the answer is yes. Okay, so like a third of you. What about who thinks the answer is no? Like 2/3 of you. Okay. So we did not reach consensus. Try, if you strongly feel one way or the other, try proving it. Or construct a counterexample. It's fun. Ish. All right. Good. Okay. take 30 seconds, take a breather, and then we're just going to do a multiple integral or two because you've technically got me for another 10 minutes. Okay, let's start with something easy, just to remind ourselves, but also to see a really important application of multiple integration, particularly for anyone going into either statistics or applied math, where probability theory plays an incredibly important role, although as the pure mathematicians will learn, they don't get to escape from it either. A practical example is joint probability distributions. You have probably met a normal curve, and probably in grade 11, do they still use tables in high school? Yeah, cool. So you probably pulled out your tables, you figured out your A and your B, and what you were doing was integrating the area under a curve that you couldn't integrate exactly, but adding stuff up. Turns out the real world has more than one thing happening at any given time. So we have what are called joint probability distributions. So in this case, your probability distribution is a curve in x and y. So here I've drawn some kind of terrible normal in both directions kind of curve. Okay, so it was pretty easy to understand how you calculate the probability of something happening here, but for a curve in x and y, that's a little bit trickier. Well, it's kind of not. The probability that your outcomes x and y are in some set of points D is simply equal to the double integral over that domain of f of xy dx dy. Exactly the same, right? And if you've done second year probability, you might have even met this idea already, is that you can integrate over some region of your outcome space to work out the probability of that outcome occurring. And there is no reason that that outcome has to just be one event. So if we let a joint distribution be x plus y, if xy is in 0, 1, cross 0, 1, and 0 elsewhere. Okay, so it would be worth you convincing yourself that a very important fact about probability is true, which is to say that the integral from 0 to 1 of the integral of the iterated integral over our domain is equal to 1, which it has to be for this to be a probability distribution. A really neat question is to give you some awful distribution, stick a normalization constant out the front, and then say, what does this have to be for this to be a valid distribution? That was almost your assignment question 4. But then I landed on the one I gave you instead, so you're welcome. Okay. So what does this joint distribution look like? So the joint distribution lives on the square 0, 1 to 0, 1. And at x equals 1, y equals 0, it has height 1. And at y equals 1, x equals 0, it has height 1. So let's connect those up. And then at 1, 1, it has height 2. So it's something like this, where these connect down that way. And as you can imagine, the probability distribution is a lot higher up this end. So it seems like our outcomes are much more likely to be in this corner here. So let's ask, what is the probability that the sum of x and y is less than or equal to 1? So what we're saying is, what is the probability of our outcome lying in this corner? And given that our probability is higher here, we sort of expect that it might be less than a half, because it seems more likely that it will land in this corner. But we don't know how much. We can do a bit of guesswork, but we should probably calculate this. Okay, so as we have to do, we're going to figure out our calculation range. And I'm going to say I'm going to integrate along x first and y second. Given the symmetry, you can probably guess there is absolutely no difference between doing it in the other way, but sometimes you just got to pick a direction. Okay, so I want to integrate along y equals 0 to 1. And x is going to have to start clearly at 0, go over to the right, and end on this curve here, which is, of course, y equals 1 minus x. So in this region, I have x plus y is less than or equal to 1. In this region, I have x plus y is greater than or equal to 1. So this is the integral from 0 to 1 minus y of x plus y dx. Integrate that out, 0 to 1, x squared on 2 plus xy, 0 to 1 minus y. And the reason I'm doing this one is just to remind you that it is totally expected that we would get y's in our answer to this integral, but not x's. This gives me the integral from 0 to 1 of a half minus y squared on 2 dy, which, when you evaluate it out, is equal to a third, which is less than a half. So that's quite nice and very believable. When you do anything to do with probability, there are quantities that you can calculate. Just finding where I've done this. And maybe you might want to say, well, what is the expectation? You know, what is the expectation of x? What is the expectation of y? So yesterday, Robbie taught you about calculating the center of mass of an object, and weirdly, the calculation is almost exactly the same, which sort of makes sense when you think about probability as a density function. So let's pull this up. Expectation of a joint distribution. So the formula for 1D, which maybe you didn't see in high school, but hopefully you've seen by now in your life, is that the expectation is the integral of x times the probability of distribution. So how much of the stuff is at any point x? And you can see here that I've written two things. So now we want to talk about the expectation of outcome 1, x, and the expectation of outcome 2, y. So the expectation of x is the integral of my region of x times by f xy dx dy. And the expectation in y is the integral of y fxy dx dy. Now you might guess in this distribution that we just did that these would be the same. This is completely symmetrical. And you would be correct, good instincts. But you calculate them out in exactly the same way, except now the domain is the whole probability space. So given that our probability distribution lives on 0, 1, 0, 1, we don't even have a difficult parameterization to do. We have the integral from 0 to 1, integral from 0 to 1 of x plus y dx dy, which is equal to an even easier integral because we would expect nothing to come out of the bounds, which is the case, which is the integral from 0 to 1 of 1/3 plus y over 2 dy, which is equal to y over 3 plus y squared over 4 from 0 to 1 equals 7 over 12. And by symmetry, the expectation of y is 7 over 12 too. Probability distributions and all of the many, many moments that you'll learn are all just extensions of multivariable calculus. When we learn about Fourier transforms and the like, you'll understand that there are all these quite strong connections between the two. Okay, it's 10 to. I'm going to let you out a few minutes early, but the one thing I want to hit you with before you go is that you have a Canvas quiz this week. I know you had one last week. After this, so it's week 4, and then I think it's week 6, week 9, and week 12. So just don't forget that. I am fully expecting like 20% of the class to forget to do this quiz. It's not trivial, but it is doable. And that brings me to a very important point about the Canvas quizzes, which came up on Ed, and I actually want to reinforce here. The Canvas quizzes are straightforward. They are not a measure of how well you will do on the exam. The Canvas quizzes are for me to make sure you have a pulse, that you are still like occasionally checking your emails, but a better measure of where you are at is assignments, mid-semester tests, and the tutorials. So use those to gauge the current depth of your knowledge, and you'll be in pretty good shape. All right. I'll see you in like an hour. I'm going to use the next hour to look at the computer sheet for the first time. Thanks very much, guys.
So in math equations, you have a sort of C or the vector. Is that, are they just like crossing out the two D?
We're going to get to that. Give yourself a week, and if you still have that question, we'll interrogate. Hey, how's it going? Well, so it was only the prelim. So as I said, I can take this off, it's fine. It's just to avoid the double dipping. The actual nasty stuff.
Oh my god, you're back to next.
No. Well, I'll be here on Wednesday. I'm used to it. It's not invasive, so thank you for your help.
Also, the Canvas, the one that came this week, is the content
Multiple. You could do it from last week.
Oh, so you don't think I can do the Canvas quiz that's out now? Oh, so it kind of covers up till the yeah. Okay, great.
Good.
Thank you.
No worries.
I can also just send that.
Regarding the question you said about like they can change the time of the value of the line, I think the answer is they can change the time.
Hold on to that thought.
So if you give me like a curve with like an orientation, then it's only one answer. But if you don't give me an orientation, then I can say one parameterization or from one endpoint to the other.
Hold on to that thought. You're thinking it. But I will explicitly address that answer. Correct. Sorry?
See you in an hour.